Hi, everybody. My name is Dan Lustig. I am a senior research scientist at NVIDIA, where I work on our GPU memory model, but I also am the chair of the RISC-V memory consistency model task group. I also have a PhD in this stuff. I'm one of the few people out there in the world who actually legitimately enjoys studying and working with memory models. So I'm happy to talk about all of this stuff in as much detail as people want to afterwards. But my goal for this talk is not to scare everybody with a tremendous amount of ugly details about memory models. But really, what I'd like to do is just give people an idea of what's in the current memory model spec that we put out for RISC-V. We put it out actually last week. It's currently up for ratification. So like I said, I want to explain some of the language, some of the intuition behind what's in the memory model spec, so that you can read it, and then if you have any questions, come up to me while I'm here at the workshop, or put them out on the mailing list so that we can explain everything. Here's kind of an agenda here. We have some background, I guess, and then we'll get into what's actually in the RISC-V memory model itself. We call it RVWMO for RISC-V weak memory ordering. I'll explain what that means. We have a couple of extensions that have separated out a couple of features that were previously in line in different parts of the spec. We separated them out and gave them their own name, ZAM and ZTSO. So we'll come back to those a little bit later towards the end. I'll explain some of the documentation that we have, some of the tools that we've put out and made available. Some of the more commonly used tools in the memory model world have now also been ported over to RISC-V. And then with that, I'll wrap it up. So first of all, let's talk about what is a memory consistency model, right? There's a lot of different notions that people have in their heads sometimes about what it actually means. It could mean ordering, it could mean fences, it could mean a lot of different things, right? Well, ultimately what it's trying to do is answer this question, which is what values can loads of memory return? Which values are legal to return, which values are illegal to return based on just what's been happening in the program as it's executing, what other stores and loads might have happened, what fences you've stuck in, and so on. Right? So all of that information about ordering and fences, it's all really meant to answer this question. What values can loads return? Right? And so why do we need this? Some of you might think it's just to give everybody a headache. I know this is not everybody's favorite topic, so like I said, I want to make this accessible. It's not meant to scare anybody. I'm going to try to bring along everybody with a lot of intuition. So rather than saying that, let's say what it actually is there for, right? We need to have a specification for what these values can be, even though it's often confusing. There needs to be some set of rules that defines what's legal, what's illegal. And right, just like all the rest of the specification, rest of the ISA spec, the privilege spec, and so on, right? It's the set of legal behaviors. This is just one small subset that tends to be separated out because it's kind of an area of study in and of itself. There's enough complexity going on. It's a nice, easy piece to decouple, so it's isolated into its own field of study. But it is meant to be integrated with the rest of the specification, obviously, and also with the formal spec task group. So Thomas, wherever he went, is going to present on that a little bit later. But like I said, this is one portion of the specification that just in general tends to be decoupled and isolated. OK. So this is not meant to be anything more than just a high-level summary of some of the different memory model options that are out there. And obviously, there's a lot of different choices. There's a lot of history. There's a lot of confusion. So this isn't meant to imply anything good or bad about all the different choices. This is just meant to give some idea of what's out there, right? So many of you have probably heard of sequential consistency, which I have up there at the top, right? It's pretty straightforward to understand what's going on there. It's about as easy as it can get for this type of memory model. But the problem is that it tends not to be super easy to implement at high performance. And so you don't really see many processors that are sequentially consistent out in the wild compared to weaker models like TSO, or ARM, Power, or whatever, right? So TSO, total store ordering, is another one that's also pretty popular, right? It's what x86 uses, what SPARC used. And so in that case, I put it over on that side, right? It's a relatively straightforward model as far as memory models go. And then within that range, there's a balance between performance you can get out of a memory model versus how many transistors you want to spend doing all kinds of sophisticated speculation-based techniques and so on to deliver that at high performance, even though TSO tends to put more restrictions on the hardware than some of these other models, right? Then on the other side, right, there's memory models which are far more complicated. So IBM Power, it tends to be a little bit more complicated from the CPU world. We at NVIDIA we embrace this challenge of weak memory models because it really gives us a lot of great performance. So I put a line in here that's kind of a cliff. It's called so to the left is multi-copy atomicity, if you've heard that term. To the right is non-multi-copy atomicity. There's a pretty big gap, pretty big jump in performance, pretty big jump in complexity as you go from the left side of the line to the right side. So we at NVIDIA embrace that, like I said, but for RISC-V, we chose to span somewhere in the middle here to the left side of this cliff. So it's weaker than TSO. It's, like I said, that's why we call it RVWMO, weak memory ordering, but it's meant to span kind of anywhere within this range. So it's a little bit easier sometimes to build and get the high performance, but it's still meant to be also accessible to programmers that want to actually use it. Okay. So here is what we call a litmus test. It's commonly used in the memory model world to understand what the rules actually imply for certain concrete situations of interest, right? So in this case, you would say, or in this particular example, it's known as the message passing example. It's generally the first one that people see. So on the left-hand side here, you would have two different stores separated by a fence. So you do a store to address X, and then a fence, and then a store to address Y. And then on the right-hand side, you have a load of that address Y. You do a spin loop to wait until you actually see a value that's not 0. So you're waiting to see the store that happened on the left-hand side. You do a fence, and you do another load of the original address X. And in this case, and like in all other litmus tests, the question is, what are the possible outcomes you can get out of this, right? What are the possible values that could be returned by loads in this program? So in this case, based on the way I drew it up, the only possible outcome, because you have the spin loop and because you have the fences there, this one, without getting into all the rules and all the complexity, this is generally one of the more intuitive cases here. So it's pretty straightforward generally to see that this one would be the only outcome. However, on the other extreme, there are cases where even having spent now a year in this memory model task group that we don't necessarily know what the answer is. There's a lot of really obscure code that can be written. It gets really complicated when you have axes of different sizes, different widths, and partially overlapping axes all mixed in there. So it can get really challenging. I'm not going to go any more detail into what's in there and what's in this particular test, but there is more information about it in the spec if you are actually curious what's going on there. But like I said, I'm going to focus on the more straightforward aspects here. Okay. One thing I want to also say, last thing before I actually jump into the rules themselves, but this is a really important point here, I think, is this notion of architecture versus microarchitecture or architecture versus implementation, right? So there's a lot of things that in the rules that say you can do this or you can't do this. But really what that means is it's only there to define the particular set of behaviors that are allowed or not allowed. The implementation under the covers can do whatever it wants to. It can speculate past a lot of things. You might have all kinds of different implementations. You might have software implementations. There's all kinds of crazy stuff you can do. And all of that is legal. By design, no memory model rule is meant to say anything about what you can or can't do in the microarchitecture, other than to say that the set of behaviors, the set of outcomes that you get out of the model, or out of the implementation, have to be legal according to the rules that are set out. So the rules are designed with a number of common microarchitectural optimizations in mind. They're designed to permit things that give more performance. But there's a lot of stuff that it's also intentionally designed that with the understanding that microarchitectures are going to do a lot of speculation because that's where a lot of performance comes from sometimes. Right? So this is a very important distinction that I want to make. Okay. So now, as I jump into actually describing the contents of the memory model, you might notice in the spec, or if you've seen some of the other literature out there, that there are a number of different ways to define memory models. And so at the hardware level, at the ISA level, there tends to be two approaches that are somewhat predominant now. there's not necessarily one that's better than the other. They just are both out there. They have they each have their pros and cons. So we made an explicit decision from day one not to try to focus on one versus the other and start a war about which one is better, kind of like Vim versus Emacs kind of war. But instead, we put a lot of effort into actually having both. And so we have actually two different versions of the axiomatic model formalized. We have one operational model formalized in addition to our rules that are in natural language in the spec. So we have all of the above. And what I want to do for the rest of my talk is walk through all the different pieces here using both side by side so you can get a sense for how each of them works individually and also how the two different pieces relate. So an axiomatic model, you basically define a set of rules or axioms or constraints, whatever you want to call them, and an outcome of a particular program, a litmus test or whatever, it's legal if it satisfies all of those axioms. If any of the axioms are violated, then that outcome is not permitted. So everything is permitted by default, but you start slicing out outcomes that go against these rules here. On the other hand, the operational model, the operational approach is to create an abstract machine model of your system. You write it down on paper, you execute it just by stepping through your highly idealized machine. And any outcome that you can get by executing this golden operational model is legal, and any implementation has to match those outcomes. Right? So in this case, it's the opposite of what I said for axiomatic. Everything is forbidden by default unless you can actually produce it by this operational model, this golden machine model that you've created. And so there's a little bit of tension there. Sometimes that makes life a lot more complicated, but sometimes it also helps us actually resolve some of the more complex cases that come up, some of the really obscure gray area that sits in the middle here. Maybe it's not code that anyone ever actually writes in practice, but we still have to have the rules for it, and we still have to say yes or no one way or the other, right? So sometimes this tension is actually good at helping resolve that. We mentioned sequential consistency earlier. Hopefully many of you are familiar with it, but here's how you might define sequential consistency in two different ways. One operationally, one axiomatically. Right, so on the left-hand side, the axiomatic style, you would say that there's a total order over all of the memory operations in the program, all the loads and stores. You would say rule number 2 is that the total order in number 1 respects everything in program order. Program order is the order that everything is laid out in the original code of the program. And then number 3, number 1 and number 2 are what you often see when sequential consistency is defined, but number 3 is an implicit rule that's actually there, so I'm going to make it very explicit because it, I think, helps helps everyone understand what's going on. So rule number 3 there is that loads return the value of the most recent store, where most recent is defined according to that total order, right? So hopefully that's, like I said, familiar to many of you, but you can also think of this in the operational style, and you can see side by side which parts overlap. So if you take the operational approach for rule number 1, what used to be a total order, now you can think of it as just all the different hearts in a machine executing, just taking turns in some unpredictable order, executing one instruction at a time. So the equivalent to number 2 is the fact that the processes are completely in order in this model. Rule number 3 turns out to be the same, right? The load values that get returned are the ones that come from the most recent store to the same address according to the sequence of events that have been executed by rule number 1. So I'm starting with sequential consistency to get kind of a starting point. I'm going to work now towards RVWMO. In the meantime, I'm going to use, before I get there, let me call out some terminology that's useful. So, and this is the terminology that we use in the spec as well for RISC-V. So on the top here, we call this total order, the global memory order. In the middle here, we have the subset of program order, which is preserved into the global memory order. That's called preserved program order, or PPO. In sequential consistency's case, that's all of program order. In other memory models, PPO gets weakened, so not every part of program order gets into preserved program order. And then this rule number 3 at the bottom here is called the load value axiom. So I'm going to use these terms as we go forward. Okay, so the global memory order is this total order of loads and stores. We have that even in the RISC-V model, but I want to zoom in on what exactly it's saying, right? Because if you go back on what I was showing on the previous slide, there's a lot of different events that can happen as a load or a store is executing, right? And in practice, it's working its way through the pipeline, it's entering the store buffer, it's entering the caches. There's a lot of different steps along the way. So if you think of what's actually useful, what's actually the most relevant point here for defining what happens with loads and stores, it's really those two bullets here that I've highlighted, right? Ultimately, like we said, the answer that we're looking for at the end of the day is about what value gets returned by loads. So it would intuitively make some sense that the point in time that we're interested in capturing with this total order is the point at which a load determines its value, right? It's looking back in the total order at that point and finding the most recent store. And likewise, on the other side, for stores, the point we're interested in is the point where the store becomes globally visible, because that's when it's now visible to loads, which are the question we're trying to answer, right? So even once we start adding in more relaxations and more complexity into the memory model to make it, to get to RVWMO, these are still the 2 points in time that we're going to be interested in for loads and for stores, respectively. OK, so here's sequential consistency again. Now I'm going to jump into TSO, just so you can see how this kind of evolves into RVWMO. So here's a couple of changes that happen. So intuitively, what's going on, you can see that, well, so before I explain that, you can see that there's a lot that's stayed the same. The parts in black have stayed the same in the operational and the axiomatic style. But then there's a couple of changes that happen, which I highlighted here in red. There's a couple of exceptions in the preserve program order section, and there's a slight change to the load value axiom at the bottom. So the intuition for this, I'll come back to the rules in a second, but the intuition for what's going on here is essentially that because one of the slow parts about sequential consistency that people long ago decided to optimize for is by sticking a store buffer in between the core and the shared memory. Right? This can be a FIFO store buffer. Generally, it is a FIFO store buffer for TSO, but the basic idea is that you want to have some way to emphasize loads which are more critical, bring them back faster, and have the loads bypass stores, which are less critical. You want to just buffer the stores, get them out of the way, allow the loads to bypass them. Right? This is a very common thing. It gives you a lot of performance just in and of itself. And so for many years, this has been the first example of a performance gain which is important enough to violate sequential consistency, right? Everyone would love to have sequential consistency, but it's complicated enough. It's hard enough to get performance. You get much better performance with just a little bit more complexity. So this is kind of the first shift into something other than SC, right? So this is now a ubiquitous thing. A lot of processors, pretty much all high-performance processors, have some kind of buffering, whether it looks something simple like that or whether it's something even more sophisticated. But it's important enough that we want to understand what effect this has on the memory model, right? So come back to the rules I defined just a couple slides ago. We're interested in what happens with loads, and we're interested in what happens with stores. So suppose we do have a store which we take off the path from the core to memory, we stick it in the store buffer, and we have a load bypass that store, right? So in that case, the load is going to grab its value by either checking the store buffer or reading from memory. It's going to grab its value before the store has gone out and become globally visible, which means now all of a sudden we need to relax that constraint that we had before, that all of program order is preserved, because now we're not actually preserving it anymore. We're having some events that originally were in a certain order, they're now appearing out of order in that total order. So if we come back now to the rules with that intuition, that's what's going on here, right? So in rule number 2 on the axiomatic side, we say that the total order, the global memory order, respects all of program order, except that now we relax store to load ordering. So load to load ordering is still maintained, load to store ordering is still maintained, store to store ordering is still maintained, but store to load ordering is relaxed because that's the effect of putting in that store buffer. The other thing we do is now we modify the load value axiom a little bit to say that we check not only the latest value in the global memory order, but also we check the latest value in program order. And that is the intuition that if you look at the operational side, that when you actually are going to do a load, you would first check the contents of the store buffer to see if there's a match that you want to forward that value from before you go back. And if there's no match, then you would go out to check memory and read the value from there. So on the operational side for number 3, again, you can see how we take this kind of thing into account, right? That you put in an explicit store buffer step. So stores first go into the store buffer where they can be read by loads, and then sometime later they'll drain out from the store buffer and go into memory, right? So again, hopefully many of you have seen TSO. I'm trying to explain it in a way that is going to, like I said, lead up to the RVWMO. So this is somewhat intentional of a way of recapping things that might be familiar. Because now, and we still have these same terms here, global memory order, preserved program order, load value axiom. So now, with this framework I've set up, now you can see what RVWMO looks like. So the same changes in, from SC to TSO are still highlighted in red, but now what I have is the definition of RVWMO. Those changes are highlighted in blue here. So essentially, the only difference here is now that we have a lot more relaxations of the preserved program order. There's a lot fewer things, but there's a set of 13 well-defined things that are maintained in preserved program order. Everything else can be relaxed. You can do a lot more reordering and therefore more easily get performance out of it. And this corresponds on the operational side to a lot of different relaxations that we built into the model as well. I'm not going to have time to go through all of those. They're laid out in great detail in the spec. OK. So in a nutshell, here are the 13 different rules that we have in preserved program order. I overlap some of them just to save space. I'm going to go through them step by step just to give you a sense for what the rules are. So here we go. I'll go through left to right here, more or less. So rule number 1 says that if remember, the legend for all this, A and B are 2 instructions, 2 memory operations that are in program order, so they're laid out that way in the original program. And we want to know whether A and B have to stay that way as they appear in the global memory order, that total order over the loads and stores. OK, so the first one is when A and B are either to the same address or are to overlapping footprints. If we want to not get into all the complexity of mixed size, let's just say that they are 2 accesses to the same address, and B is a store. In that case, you don't need any other kind of synchronization at all. You can just, by rule, A would have to appear before B in preserved program order, and hence in the global memory order. That one's pretty straightforward. If you could start to reorder even stores to the same address, that would start to get really complicated, probably too difficult to even program, and so that is a pretty standard rule here. I'm going to skip rule number 2 just for a minute. I'm going to come back to that at the end just because it's a little bit more complicated. Rule number 3 is also pretty straightforward. It says that if A is an AMO, atomic memory operation, or a store conditional operation that was successful, and you have another load which is to the same address that comes later, and you read from, and the load would be trying to read from that store value, there were no other stores in between, in that case, you would not actually be allowed to forward, say, while the store conditional was in the store buffer. You have to actually maintain that ordering from the AMO or from the SC to the subsequent load as well. That helps some synchronization algorithms work properly, just preventing forwarding from an AMO which is too soon. Although I say that, but again, just to recap, you can always do a lot of speculation, and you can predict all kinds of things if you want to make things go faster. Often that's a very successful strategy, but the outcomes still have to match the rules. OK. Rule number 4, another pretty straightforward one. If there is a fence in between A and B, and you've marked the appropriate bits in the fence instruction, then you would maintain the ordering between A and B, right? So I think you may have seen this earlier. There's previous reads, previous writes, subsequent reads, and subsequent writes. You can check off which specific items you want to have in your predecessor set and your successor set if you want to just narrow in on a particular fence. There's also the I/O equivalents to all of that. But again, that's a relatively straightforward rule, that fences do what you would expect them to do. Rules 5 through 7 are the release consistency rules that we have. attached. So we have the .aq and .rl bits that are attached to AMOs and load reserve store conditional instructions. If you have an acquire, it orders, the acquire is ordered with everything after it. If you have a release operation, everything before the release in program order is ordered with that release. And then we're very specifically we chose to implement the RCSC variant of release consistency, which says that the synchronization operations themselves, when marked as such, are also sequentially consistent, which means in this case, we have to fill in this missing ordering that if we have a release followed by an acquire, there's also an ordering there. There are other variants of release consistency. There's a lot of different variants out there, but we chose RCSC for this. Going to skip rule 8 also. I'll come back to that in just a second. Rules 9 through 11 are syntactic dependencies. There's a few different variants. There's an address dependency, a control dependency, and a data dependency. So an address dependency is where you use the result of some load, maybe do some arithmetic on it, and then use that outcome as the address of some subsequent load or store operation. Data dependency is similar, except you use it as the data value being written by a store, some subsequent store. A control dependency is when you have a value returned by a load that feeds into a conditional branch that determines whether some subsequent load or store is even executed or not in the first place. So all of these things also, as it turns out, need to be maintained. That's a standard property of modern memory models, at least from the CPU side. Programmers, maybe systems programmers, tend to use this trick a lot. It's a lighter weight form of synchronization that really zooms in on just those specific instructions in question. So this is one thing that was not in the original memory model spec from way back. So this is one big new piece that we did add in to make sure that we're compliant with C++ and Linux and all the other important software packages that do sometimes rely on details like this. So we've added those in. Rules 12 and 13 are somewhat compound combinations of some of the other relations that I've mentioned so far. So address data reads from, essentially for the purposes of this talk, I'm not going to get into it too much other than to just say that we have them in there. If you're curious, come up to me and I'm happy to talk about them in more detail. They're really not super commonly used. They're just something that needs to be in there to ensure both that the axiomatic and operational models align, and also that there are some obscure cases in operating systems which do use them sometimes. So we put them in there, but if you're not actually specifically focusing on memory models, you probably don't need to spend much time worrying about it. And then lastly, rule 8, which I also skipped earlier. I have one more after this, but anyway, rule 8, this one is mostly redundant with rules 1 and 11. This one says that if you have a load reserved and a store conditional and they're paired with each other, the load reserve has to appear before the store conditional. This only ever actually comes up if you have mismatched addresses, which is another side topic here. Finally, rule 2, this is one I skipped way back from the beginning. So this one is same address load to load ordering, which turns out to be more complicated than all of the other same address options. Same address combinations. And the reason for that is these two scenarios here. So in general, if you have an older load followed by a newer load in the same thread back to back, the newer load is never going to read an older value, but if they do return the same value, there are common hardware optimizations that would allow those to appear to be reordered. Right? You can do the second one speculatively and then come back later and figure out that the first one reads the same value. That's common enough that we chose to keep that in the memory model like other architectures do. So it's a pretty standard thing, even though it's not necessarily the most intuitive and obvious rule in the world. There's also another scenario where if you have a load, a store, and a load all to the same address, and that latter load forwards from the store buffer, that can also appear to have executed and have grabbed its value before the first load did. And so it's another common architectural feature that, as it turns out, is common to put into the memory model, so we also did that as well. I'm obviously kind of rushing through this a little bit. My time is already running short. But like I said, we have all kinds of explanation in the spec, and I'm also happy to take questions afterwards. OK, so that was a whirlwind tour of all the different preserved program order rules. Rick is already walking towards the stage, so I'm going to speed it up here. We have atomicity rules here. AMOs are single events in the total memory order, in the global memory order. Those are pretty straightforward. We have a rule that says essentially that if you have a load reserved and a store conditional and the store conditional is successful, you can't have another store from another heart that appears in between the two. Just a pretty standard definition of atomicity there, so I won't belabor the point. There's other constraints on LRSC just to make sure that they will succeed eventually. There's also a progress axiom, which is a theoretical necessity, just to make sure that you don't completely starve any one individual heart, but it's not intended to be any notion of fairness or forward progress guarantees or quality of service or anything like that. It's intentionally not any of those. Okay, and that's it. That's RVWMO. We have two extensions, misaligned atomics. If you may have seen that in the spec, we separated that out. There's also ZTSO. So if you do have TSO-only code, there's now a way to express the fact that your core is in fact TSO inherently, also called out separately, so you can query that per implementation. Lots of ongoing future work, lots of documentation in the spec. It's all pushed, it's all upstreamed, so check it out. Our 45-day clock has started as of last week, so please do take a look. If you do have any comments or need to run it by people before it becomes ratified, goes up for a vote in a month or two, now would be the time to do it and send the feedback either to me or to ISA Dev. Put it up as an issue on GitHub. Any way you want to pass it along, we're happy to take a look and answer questions. And that's it. So thank you.